So in this video we are going to learn about oxo process. So this is also called hydroformylation reaction. So in this case formyl group is nothing but CHO and then hydrogen is hydrogen. These both groups are added in an alkene, okay? C or CH double bond CH2. In this case, consider initially hydrogen is added in this first carbon and then CHO is added in this second carbon. The product will be or CH2 single bond CH2 and then CHO will be present. So this is one of the product. There is also another way where in this here CHO is like the opposite. Here CHO is added and here hydrogen is added. Then the product will be or CHO and then CH2 CH3. So this will be another product. Okay, so here this one is branched product and this one is straight chain product. So mostly we prefer to have straight chain product because it is more biodegradable. Okay, so we are exchanging, like preparing so many different catalysts to make more selectivity to give straight chain product. What is meant by selectivity? Like we need 90% of straight chain and 10% of branched. Okay, either cobalt catalyst or else rhodium catalyst is mostly used. Some other transition metal catalyst also can be used, but most preferably these two catalysts are used. Later on we will learn in detail about their selectivity, like rhodium is really very much selective than cobalt. Okay, first we will learn about the mechanism of this cobalt complex. Okay, CO means this is carbonyl group. Okay, so this carbonyl is actually a ligand. Okay, CO8 is present and then cobalt is present 2 times. So this is the cobalt catalyst I am talking about. Okay, so this is mainly responsible for this oxo process. Okay, so but then this catalyst actually cannot undergo this particular hydroformylation. From this we have to react it with hydrogen and then we will get H and then CO and then CO4. Okay, so this is the main catalyst. Okay, why we are not directly using this catalyst means it is pretty not available directly. Instead this is more available, that's why we are using this and then we are adding hydrogen and getting our main catalyst. Okay, so now we can check the 18 electron rule for this particular complex and then the oxidation state for better understanding. So first we will see the oxidation state. For cobalt I am taking X and then for hydrogen I can put -1, right? I will -1. Why we are adding -1? Because hydrogen has only 1 electron. If it is gaining another 1 electron it will be more stable. And then for carbonyl ligand it will be 0 because it is already stable. So they don't need any electrons. So X will be +1. Okay, so what is the hybridized, what is the electronic configuration means? Outermost 4s2 and then 3d7. Okay, here cobalt is in +1 oxidation state. So the electron will be removed from the outermost shell, that is the 4th shell. So 4s1 and 3d7 will be present. Okay, then what will happen? Totally how many electrons are there? 8 electrons are there. And then for carbonyl, for ligands, each ligands mostly they will give 2 electrons. Okay, mostly, it is not necessarily everything will give 2 electrons, but then carbonyl will give 2 electrons only. Hydrogen is going to give 2 electrons only. Okay, so only one hydrogen is present, right? Only one hydrogen is present, so for that I am writing 1 2 and then 4 carbonyl is present, so 4 2s are 8. Okay, so 8 2s are 16 17 18, so totally 18 electrons are present. So this particular catalyst is completely stable. We cannot add any more ligands to this particular catalyst, so that is the, so it is stable. So that is the problem here. Why means because we need to add an alkene into this particular catalyst so that we can undergo the hydroformylation reaction, but there is no way we can add something inside because it is already full. So in order to add an alkene, it has to be 2 electrons. Actually an alkene will give 2 electrons, so it has to be short in 2 electrons so that I can introduce an alkene. Okay, so basically if it is having 16 electrons, if this catalyst catalyst is having 16 electron means, then I can conveniently add 2 electrons so that it will become 18. Okay, but it is already in 18 electrons. So what can I do means, so the next step come into play here. Okay, so what we have to do is, we have to remove a CO group. Okay, one carbonyl group, that is 2 electrons are removed. Okay, so the step is HCO and then CO3. So now it is only 16 electrons. So here it has a space for what? Alkene. So this is the space provided for what? Our alkene group. So what is the hybridization for this particular group means? DsP3, that is trigonal bipyramidal structure. Okay, trigonal bipyramidal structure is there initially. Okay, so I hope you know how to find the DsP3 structure. Okay, then it is coming to this particular structure. There is a vacant space for what? Alkene. That's why we have made space. So now who will react? Alkene is going to react. Okay, CH2, and then here one hydrogen is present. So now what we have to do, this alkene is having 2 electrons and it is reacting there. Okay, hydrogen, CO and then CO3, and then one alkene group is present. Okay, alkene group is present. So instead of writing it like this, let's write it more understandably. Okay, so here see, I'm just representing it. Okay, in a structure form. Okay, C double bond CH2 and then C or and then H, and then here this is trigonal bipyramidal structure. Okay, 5 ligands are there, so trigonal bipyramidal, and then I am writing one hydrogen here, 3 carbonyl groups are present here. Okay, so it is having DsP3 configuration. Okay, hybridization. Okay, now what we have to do is, the first step is migratory insertion. Consider this is the first carbon 1, and this is carbon 2. In these 2 places migratory insertion is taking place. Okay, so what is happening is, see this hydrogen along with this 2 electron, is going and attacking in carbon 1, that is this is the first carbon, it is attacking here, and then here 2 electrons will be present in this bond, right? That 2 electron is going and attacking our metal. So this is for migratory insertion, first step of migratory insertion. Okay, in migratory insertion there are 2 steps available. Okay, so first one ligand is attacking another ligand, that is the first step. Okay, so cobalt is present, CO is present, and then CO is present. Here this hydrogen space is now vacant, and then here what is happening? CH or and then CH. So this hydrogen is bonded. Okay, now the second step of migratory insertion is, what is happening is, this entire bond, that is this entire bond is going to the place where the hydrogen was initially present. Okay, that is the second step of migratory insertion. So this entire compound is going to this empty space from where the hydrogen was removed. Okay, so we can write it. CO cobalt is present, 3 carbonyl group is present, and then here now a vacant space will be present, and then here CH or and then CH3 is present. So this is migratory insertion. So there are 2 migratory insertion in this particular mechanism. So the first migratory insertion is over. Okay, in migratory insertion, what was the first step? Initially the hydrogen ligand will go on any ligand. Basically migratory insertion means what? A ligand is attacking another ligand. Okay, so this hydrogen ligand is attacking another ligand, and then this newly formed ligand is going to the space where the initial ligand was present. These are the steps of migratory insertion. Okay, so now what we need? So now calculate the total number of electrons in this case. What will be the total number of electrons? So the oxidation state of cobalt will be plus here also, because for this entire group it will be -1. So the oxidation state will be CO plus. So 4s1, 3d7 will be present. So basically 8 electrons are present. And then these three things will contribute to 2 electrons each. So 3 2s are 6. Okay. So how many electrons are present? 12, 13, 14 is present. Okay. 14 is present. Then along with this, this is also giving 1, 2 electron. So totally how many electron is present? 16 electrons are present. Okay. So now next step is what we already saw in initial reaction, that in one carbon we have to add what? In one carbon we have to add our this hydrogen, right? In one carbon I have added this hydrogen, that is over. In this next carbon, what I have to add? I have to add CHO. So for that, first we are going to add CO and then we are going to add hydrogen. Okay. So for adding that CO, we need CO, right? CO, if there is a CO, we can add CO. Okay. So for that, we cannot use these CO. Why? Because already 16 electrons only is there. So if you are removing this CO and going to add there will be only how many electrons? Only 14 electrons will be there. That is not a quite good structure. So instead, what we are doing is, we are adding another one carbonyl group. Okay, so CO, and then here CO group is present, CO group is present. In this empty space, I am taking another one CO. It is added, okay. Remaining this alkyl group will be present, or CH3 is present. Now extra CO is there. Now this will be how many electrons totally? It will be 18 electron complex. Okay. So from here what we are going to do is see this structure clearly. See C triple bond O. It will be present like this. Okay, it will be present like this. What I have going to do is, this bond is having 2 electrons, right? So this 2 electron is going along with this entire thing, is going and attacking this carbon. Okay, and then this one of the bond is reaching here. Okay, so this is the reaction. So this is also called what? Next step is also called what? Migratory insertion. Okay, so 2 migratory insertion are happening. Initially hydrogen was migratory happened, and now CO group. Okay, so what is happening? This 2 electrons along with the entire group is attacking the carbon, and then this bond will go there. So now what will be happening? CO, upside there will be empty space, CO, and then here C double bond O. Here what is attached? That CH group, CH, and then one OR group is present, and then CH3 is present. So this entire group I have written in that C part. Okay, that is the reaction. So now moreover everything is completed. Okay, we have bonded this hydrogen, we have bonded this CO group also. Another one group we have to bond, that is what? Hydrogen. Another one hydrogen is present. I need it here. Okay, basically I need an aldehyde. Okay, so what I have to do is, oxidative addition of hydrogen is happening. Okay, so then what will happen? In the cis position, 2 hydrogen is added. Okay, so 3 CO group is present, and then this entire group will be present here, CO, CHR, and then CH3 is present. So this is oxidative addition of hydrogen, because we need hydrogen. Okay, then what will happen is reductive elimination. What is happening? Reductive elimination is happening. So what is mean by first reduction? So first, what is mean by oxidation? What is happening here? I told this is an oxidative additive step, right? Oxidative. So oxidation means loss of electrons. So the oxidation state is basically increased. Okay, see, if we check here, consider in this case here, what will be the oxidation state? X will be what? +1. Okay, so because this entire group will be -1, so it is +1. So what is the oxidation state here? X is equal to +3 will be there, because this hydrogen will be 1 -1, hydrogen is -1, and this entire group is -1. So oxidation state is increased by 2. Okay, so that's why it is called oxidation. Another thing we have to notice is that here the coordination number is how many? 4 ligands are attached. The coordination number is 4. But in this case, the coordination number is what? 6. See 1, 2, 3, 4, 5, 6. So totally 6 ligands are directly attached. So basically the coordination number is increased by 2 and the oxidation state is also increased by 2. That's why it is called oxidative addition. In the case of reductive elimination, basically the cobalt is going to gain electron. It is basically going to gain electron so that it will be reduced. So the oxidation state is going to be what? Reduced. See, what is happening is this bond is having 2 electron. This bond is going and attacking our hydrogen. Okay, then what is happening is this bond is there. There it has 2 electron. That 2 electron will be given to our metal cobalt. Okay, so that is why the metal is reduced, because it is gaining electron. So what will be the remaining structure? CO is present. 1 hydrogen is there. 3 CO is present, and then what is the further product? CHO. The aldehyde is now formed, and then CHR and then CH3. So this is the what? Aldehyde, that is the hydroformylation products. So it is like a very easy overall reaction. So initially what is happening? So initially we have the over a main catalyst. From that we are getting another catalyst. So this is the main catalyst. So here this is like a precursor. We can tell this as a precursor catalyst. And then what is happening? We are removing one carbonyl group, and then we are going to add this alkene group. And after alkene is added, what we are doing? Migratory insertion for hydrogen. So here migratory insertion is happening for hydrogen. First migratory insertion is happening, and then we are adding another one carbonyl group, and then second migratory insertion is happening, and then oxidative addition of hydrogen, and then finally reductive elimination of the entire aldehyde group is happening. Okay, so basically this is the main steps. So there are some limitations for this cobalt catalyst. Okay, so what is the main limitation means? We already saw straight chain product will be formed, or what will be formed, or this branched product will be formed. We already saw, right? So in the case of cobalt catalyst, it will be formed in 3:1 ratio. So what is mean by 3:1 ratio? So basically 3 divided by 4, consider totally 100% is present, it is 75. And then 1 divided by 4 into 100, it is 25. So if straight chain is 75%, branched is 25%. So this is not a very good selectivity. We need more percentage of straight chain. So this is a main disadvantage of cobalt catalyst. So and the temperature is also very high for this reaction, like around 140 to 175, and the pressure is also high, like very high, 200 to 250 atmospheric pressure is there. So these are all the main disadvantage. For this there are some replacements. Okay, what they did is, so this is the main catalyst, right? CO4. Cobalt, this is the main catalyst. Instead of one carbonyl group here, they try to replace it with a butyl group. Okay, PBU3. Okay, tributyl phosphine. They replaced it like this. So the product is CO3 and then PBU3. So this is the newly formed catalyst. So this gave a pretty much good result than this earlier one. So the selectivity was around like 9:1. For straight chain it was 9, and then for a branched it was 1. So 9:1 means 9 by 10. 9 by 10 into 100, it is 90%, and then 1 by 10 into 100, it is 10%. But still scientists were not satisfied by this selectivity. They need more percentage of our straight chain compound. So what they did is they introduced rhodium catalyst. Okay, rhodium catalyst, HCO, and then only one carbonyl group is there. Only one carbon, and the rest 3 carbonyl group is replaced by any other alkyl group. We can write triphenyl phosphine, or we can generally write H or H, CO, and then instead of PH I am just writing OR3, or represent any alkyl or aryl group. Alkyl or aryl group. So this is the main thing. So this gave high selectivity. The selectivity was like around 16:1, like super selectivity. Okay, so initially the cobalt catalyst gave only what 3 is to 1 percentage. After that they replaced one carbonyl with PbBu3, then it gave around 9 is to 1 ratio. And then after using this rhodium catalyst, they had only one carbonyl group. Rest every carbonyl group is removed and then replaced by this triphenyl phosphine or any other any other alkyl phosphine group. They give high selectivity. And there is also another advantage for this particular complex. It is that it can even operate in low temperature like around 90 to 120 degrees Celsius, and the pressure is also pretty low for this particular catalyst. So now we are going to learn about this particular catalyst, the mechanism, the same mechanism like the cobalt catalyst only. Okay. So this is the complex rhodium, and then hydrogen is present, and then one carbonyl group is present, and then PPH3, PPH3, and then another one PPH3. So this is trigonal bipyramidal. Okay, trigonal bipyramidal structure. Then because totally how many ligands are present? 5 ligands are present. Okay, and then the hybridization will be DsP3, the same. So what is the what is the electronic configuration for rhodium? 4d8 and then 5s1. So in this case the oxidation state will be +1. Why means because only one hydrogen will contribute -1. So X -1. All other ligands are neutral ligands, so it will be 0. So X will be +1. Okay. So rhodium plus will be what? It will be 4d8 because the electron is removed from this outermost fifth shell. Okay, whether it is obeying 18 electron rule or not means it is obeying. Okay, so totally 8 rhodium is present and each ligand is contributing 2 electrons. Okay, every ligand. So how many ligands are present? 5. So 5 to 10. So totally 18 electrons are present. So it is good. But what we need to add our alkene here. So we need some space to add our alkene. So who is going to remove means this triphenyl phosphine is going to be removed. Okay, we are not going to remove anything else because triphenyl phosphine is super big. So if it is removed means there will be more space for our alkene to attach. Okay, so basically we are removing this triphenyl phosphine. So what will be the product? Rhodium, hydrogen, and then carbonyl, PPH3, and then PPH3 is present, and then here a vacant space is present. So in this vacant space only we are adding what? Our alkene group, CH double bond CH2. So our alkene group is going and adding in this vacant space. So rhodium, hydrogen, PPH3, and then carbonyl, PPH3, and then our alkene group is added here. Okay, or CH2. So now next step will be what? Next step, what we need to add? First we have to add our hydrogen group. That is the main step in everything. Okay, so it is called what? Migratory insertion. Okay, 1, 2 migratory insertion. So this is the 1 means this is 2. Okay, so what will happen in migratory insertion? Basically this hydrogen here along with its 2 electron is coming and attacking this first position, and the 2 electrons in this bond is going and attacking our rhodium. Okay, so this is migratory insertion. So migratory insertion has 2 steps. The first step is over. Okay, rhodium, and now here a vacant space is present. PPH3 is there, CO, everything is same. Okay, PPH3, and here what is happening? Here this CH or will be present, and then here CH3 because extra hydrogen is added here. Now what is going to happen means this entire bond along with this is going to attack this place. So this is a step for migratory insertion. Okay, so all this entire thing is going to go there. Okay, rhodium, PPH3, and then CO, PPH3, and then CH or and then CH3. Now the vacant space is here. Now what we need to add? We have added the hydrogen. Now what is the next step? We have to add carbonyl group. So can we use this carbonyl group? Means no, we cannot use the already present carbonyl group because this compound is only having 16 16 electrons. Okay, if we remove this carbonyl group, there will be only 14 electrons. We don't need that, it is very unstable. So if you calculate it, it will be having only 16 electrons. So what we are going to do, we are going to add a carbonyl group. Okay, so a carbonyl group is added, CO and then PH3 and then PPH3, and here the entire alkyl group is present, CH3. Okay, so here CO group is added. Okay, now what is happening? Now the migratory insertion will be happening. The second migratory insertion is happening. Okay, so migratory insertion means already I have told you, right? So what is happening? This entire group is there. Consider this is like this. This entire group is coming and attacking here, and this bond will go here. Okay, so the same step. Okay, rhodium, PPH3, CO, PPH3. Here a vacant space is there, and then C double bond O. Here what is attached? This is a carbon, and then this hydrogen, OR group, and then CH3. So this is why it is called a organometallic complex. As you can see, this metal is directly attached to carbon. These are all the reasons. Whenever a metal is directly attached to metal is directly attached to a carbon group, then it is called a organometallic compound. Okay. So now what is the next step? We have to add our hydrogen, and then we have to eliminate the entire aldehyde. That is the next step. Okay. So already we have learned about oxidative addition of hydrogen. So the hydrogen is going to add in the cis form. Okay, hydrogen, PPH3, CO, and then PPH3. Downside this CO group is present, and then CH or then CH3. So what will happen now after oxidative addition? This is oxidative addition. Okay, then what is happening? Reductive elimination. So now we have to remove our hydrogen. Okay, so what is happening? This bond along with this is going here, and then this 2 electron will reach our rhodium. The final product is going to be hydrogen, and then carbonyl is present. This PPH3 is present as it is, and then this PPH3 is also there, and then COH group is there, and then CH or and CH3. So this is the final product formed. Okay, 2 products are formed. So basically cobalt catalyst and rhodium catalyst, the main difference is in selectivity and the temperature and pressure on which it is reacting. Okay, so next we can talk about the reactivity. So similar to like Wilkinson catalyst, here also reactivity is less when the steric hindrance is high. Okay, so consider a straight chain complex. Okay, CH2 and then CH or group, CH2 or double bond CH2. Okay, so consider this particular reaction. Okay, so here whether this one will be more reactive or this internal hydrogen is more. This is terminal and this is internal. So basically the terminal will be very much reactive because it is less sterically hindered. Okay, then consider a straight and branched. Consider there is a straight chain like this, something like a CH2 CH, or this is like a straight chain. Okay, in the case of branched we can consider CH2 something is like that. So straight chain will be more reactive than branched. Of course branched is highly sterically hindered, so that is less reactive. So mainly after this aldehyde is formed, this aldehyde is further reduced to alcohol, and this alcohol is mainly used for detergent. Very important application, detergents. Okay, so these alcohols are used in detergents, and they are also used as plasticizer. Okay, plasticizer means in order to like soften the plastic materials, the plasticizers. So these are important uses of this particular aldehyde. I mean from the aldehyde the alcohol is formed. Mainly they are using this alcohol for these 2 particular things. Okay, thank you for watching this video. Like, share and subscribe my video.